So now if I expand like previously to see how many equations I get. So let's say for I equal to 1, I would like to get equation for u1. Okay, equation for u1 velocity. So I get dou u1 by dou t plus, now j is repeated, so you need to sum over j, right? So I get, but I equal to should be 1, I should not be changed, I is the free index here, right? I can take value 1, 2 or 3. So we are looking into I equal to 1 means u1 velocity component, looking into the momentum along the x direction, x1 direction, and therefore j is the summation part. So you have to write u1 dou u1 by dou x1 plus u2 dou u1 by dou x2 plus u3 dou u1 by dou x3. J is summed over summation rule. J is summed over, on this side I get minus 1 by rho, the pressure gradient along the x1 direction, plus 1 by rho here, j is repeated again, dou tau ij by dou xj, I is 1, right? So dou tau 1, j is repeated, so tau 1 1 by dou x1 plus dou tau 1 2 by dou x2 plus dou tau 1 3 by dou x3. So I have one equation here for velocity u1, and I need of course the velocities 2 and 3 also, but for that I can write an expression for I equal to 2, I equal to 3, I will get equation for u2 and u3 velocity. So left hand side is completely taken care of, okay, and but I have an extra unknowns on the right hand side. So similarly if I write equation for I equal to 2, okay, equation for u2, I will not write the whole part, so you can write, so I am going to just look at this particular term here, okay. So this is 1 by rho dou p by dou x2, here it is dou u2 by dou t, and then the other term we have to write down. So here this term is important, so let us look at dou, now I equal to 2, dou tau 21 by dou x1 plus dou tau 22 by dou x2 plus dou tau 23 by dou x3. Similarly for I equal to 3, equation for the third velocity component, so it's dou u3 by dou t plus, you can write the convective term 1 by rho dou p by dou x3 plus 1 by rho dou 3 1, I equal to 3, so tau ij, tau 3 1 by dou x1 plus dou tau 3 2 by dou x2 plus dou tau 3 3 by dou x3. So we have 3 equations, right? So if I look at number of equations here, I write it here, number of equations and number of unknowns. So I have 3 equations, equation for u1, u2 and u3 from conservation of momentum, correct? So this will also help me solve the continuity equation, which requires u1, u2, u3. This is taken care of. But what are the unknowns in the three momentum equations here? So we had unknowns u1, u2, u3 that I need to solve, which is fine. In addition to that, I have pressure term, right? And then I have the last terms here. It's totally 9 terms, it's a tensor, but it's a symmetric tensor. Whether it is tau ij or tau ji, you will get the same. That is the easiest way to check whether the tensor is symmetric or not. So when you expand it, you will get the same. So we expanded it as tau ij. Now you can do tau ji and give values, you will get the same tensor. That means it is symmetric tensor. So we can look into only the diagonal components here, tau 11, tau 22, tau 33, and the off diagonal 3 components, that is symmetric. So tau 12 and tau 21 are the same. So we can look at this. So I get 6 unknowns here extra, which is tau 11, tau 22, tau 33, 3 normal stress terms, okay, and then 3 shear stress terms, which is tau 12, tau 13, tau 23. So I get 4 plus this 10 unknowns. So now for pressure, those who have studied CFD would know that you can use continuity equation to solve for pressure, okay. So that is kind of taken care of. So if I say continuity equation will help me, this particular term, using continuity equation. So this can be taken care of. Either if you know the method, like let's say simple or something like that, you can do that, or one can also derive an equation for the pressure term. We would need that as we go into deeper into the turbulence modeling. We will derive that equation later. Right now it is not required. So one can also derive an equation for pressure, which is called Poisson equation. Using continuity and the momentum equation, one can derive that, okay, and solve that. That is also possible. That is used extensively in CFD techniques, that route. So in any case, we have 4 equations in total, right? So you can say 3 plus 1. The other one is this continuity. So 4 equations are there, 4 unknowns are taken care of, but the additional unknowns is this part. This is the extra unknowns that is causing the problem. 6 extra unknowns. So when number of equations are lesser than the number of unknowns, okay, number of equations is less than number of unknowns. What do we call this? Closure problem. Mathematicians call this a closure problem because you cannot solve the simultaneous equations when number of unknowns are more than the equation. Okay, if you have 3 unknowns, you need 3 equations to solve it as simultaneous system of equations. So this is the closure problem. So what do we do? How do we proceed? We have extra unknowns. We have not even started turbulence modeling. We have not even looked at, this is just Navier Stokes equations. How do we proceed now? This you should have studied in the fluid mechanics course. Exactly. So we are using a model, right? This model, is it universal? It can be used for any type of fluid. Exactly, exactly. So you have already been introduced to a model, right? So a model is required. Is required to close the equations. So what is that model? Is Newton's law of viscosity for a Newtonian fluid. Okay, so for a Newtonian fluid, using Newton's law of viscosity. So what does this model tell us? This model tells us that we can relate stress to the strain, right? Stress proportional to the strain rate. This is the model here. Okay, so if I apply that Newton's law of viscosity, so I get Newton's law of viscosity, which is tau ij is equal to 2 nu Sij minus 2/3 mu dou uk, or I can simply say skk. So where Sij is the strain rate tensor. Sij is your strain rate tensor, which is equal to half of your dou ui by dou xj plus dou uj by dou xi, your strain rate tensor, and skk implies I equal to j. Okay, so skk will give me dou uk by dou xk here, that component. Okay, or we can simply say can simply use dou uk by dou xk also, and by continuity it would go away. So whenever we use incompressible flows, that is constant density, this term will vanish because its dou uk by dou xk is 0 by continuity equation. We would have only this part. So we have related the stress to the strain here, and this is applicable only for Newtonian fluids, of course. So we already have a model. So now this was 6 unknowns, right? This is 6 unknowns is now modeled as, here mu is of course an unknown, your molecular viscosity, which you can know for a particular Newtonian fluid, so that is taken care of. And then what do you need here? Other than that, you would need the strain rate or the velocities. Basically you need the velocity, so which is known to you, right? So this is known, so 6 unknowns have been made or related to 3 known factors, and therefore the equations are closed. Okay, therefore equations are closed. So we already used a model before starting what is called turbulence modeling. So this kind of approach is also used as we go further. So we will start with one particular aspect of it, or the beginning of what I say turbulence modeling is to look at the equations for mean fluid motion and equations for fluctuating fluid motion. Okay, so this particular topic would be called Reynolds averaged Navier Stokes or called RANS equations. So in the Reynolds average Navier Stokes equations, first of course the chapter 1 part, the statistical analysis, we decompose the the flow into mean and fluctuations, right. So first part is Reynolds decomposition. Reynolds decomposition, which basically, when I talk about Reynolds, this is Osborne Reynolds, O Reynolds. Okay, so we can split, let's say, a velocity component u into its mean and fluctuation. Okay, so this is the instantaneous velocity into the mean and the fluctuation. If I do this decomposition to the equation, I am going to get an equation for the mean fluid motion and also an equation for fluctuating fluid motion. Okay, so of course this can also be, everything can be split. So one can also split pressure also, instantaneous pressure as a mean pressure and the corresponding fluctuating pressure. Okay, so now we first look into equations for mean fluid motion. Equations for mean fluid motion. This is more exciting for engineers because they are interested in mean flows, average velocities, average pressure, temperature and so on, right. But this is also useful for scientists because we can separate the mean out and look into what is the remaining fluctuations. Okay, so we have the equation 1 and 2, which is continuity and the momentum equation. So we split this equation into two parts here. Okay, we will do the continuity equation first. Continuity equation we take, which is dou uj by dou xj equal to 0. So I am going to split this into two, that is Reynolds decompose and ensemble average. This gives me dou uj bar plus uj prime by dou xj, which is equal to 0. So the operations, I can split this into two part here. I also have to average it over, right. So I have dou uj bar by dou xj plus dou uj prime by dou xj equal to 0. I also talked about not just Reynolds decomposition but also ensemble averaging. So let me ensemble average. So ensemble averaging and addition commute. So it can be written into two different separate terms. So this gives me dou uj dou xj plus dou uj prime average by dou xj. Okay, even the differentiation and the ensemble averaging commute here. So that's why the averaging operation is over the velocity component. So now what would happen? We already learned from chapter 1, the second term would go to 0, right. This is the ensemble averaging of a fluctuation. That's why I thought the difference between arithmetic mean and the ensemble mean. Arithmetic mean, it will not go to 0. So we will be struck with this term. With ensemble mean, believing that it exists, this is 0. Okay, average of a fluctuation, ensemble mean of a fluctuation is 0, that we have already seen the proof, and the ensemble averaging a true mean does not change its characteristics. So we get our continuity equation for mean motion, mean fluid motion, as dou uj bar by dou xj equal to 0. This looks fantastic. Both the equation 1, which is the continuity equation itself for instantaneous fluid motion, and this particular equation, you can call it, let's say, equation 3, the continuity equation for the mean fluid motion, they look similar. Okay, so far it's really amazing. And one can also look at the continuity equation for a fluctuating fluid motion now. Okay, so how to do that? We can also look at continuity equation for a fluctuating fluid motion. Continuity equation for fluctuating fluid motion. This is straightforward. I have this was our equation 1, if you remember correctly. I take equation 1, equation 3, right? I can subtract equation 3 from 1, correct? So I get equation 1 minus equation 3 would give me dou uj bar by dou xj plus dou uj prime by dou xj. This is the Reynolds decomposed equation 1 minus dou uj bar by dou xj. Okay, so this is equation 1 here. This part is your equation 1, Reynolds decomposed, of course. So this yields dou uj prime by dou xj equal to 0. Okay, again very interesting. So we have got a continuity equation for the fluctuating motion, also looking similar to equation 1 and 2. So we will see in the next class whether something similar happens to momentum or some surprise is going to be there. Okay, fine, thank you.